3-2, nice and quick. The development of the modern day model. First up, alchemists. Remember, they were trying to make gold or any other precious metal. Uh, weren't successful, but they set this kind of the basis for experimentation in chemistry. Describe or draw Dalton's atomic model. You should just be thinking bocce ball. He thought the atom was a solid sphere. It was indivisible, indestructible. We now know that that is not the case, but he thought it was kind of like a bocce ball, except really, really, really small. He also wrote up his atomic theory. You should know all the 4 parts of it and what's kind of right and wrong about each. Remember, he said that all matter consists of atoms. That part's great, but he did say they're solid and indivisible and indestructible because he didn't know anything about subatomic particles. So that part's a little iffy. Atoms of the same element are identical. Sort of true, they're close, but he didn't know about isotopes or ions. He didn't know you could have different number of neutrons because he didn't even know about the neutrons in the first place. He didn't even know about the nucleus, forget about neutrons. And atoms of different elements are different. That is correct. Oxygen is obviously different than nitrogen and so forth. Atoms can combine in whole number ratios, absolutely. If we have sugar, glucose here, C6H12O6, they are all whole numbers. You're not going to get a fraction of a number. So he's good there. And atoms can combine, rearrange, separate from one another during ordinary chemical reactions. True. Atom of one element can't be changed into another element. Only of ordinary chemical reactions. Like if I'm running my magnesium lab, I can't make magnesium turn into something else. It's still going to be magnesium. It might hook up with the chlorine and end up being magnesium chloride, and the little hydrogens are set free, but it's not going to magically turn into anything. That is true of chemical reactions that are just ordinary basic reactions, but he didn't know about nuclear chemistry, and we now know that you could end up taking 2 atoms and fusing them together, or splitting an atom and separating it, or letting it undergo decay and it turns into something new. So he was the first guy to really kind of sum up the idea of an atom and give scientists something to work with. And then they took his atomic theory and his ideas and they ran with it, and they found lots and lots of new information about the atom, and that theory got changed. But that was his original theory. Now here are some of the experiments that happened that changed Dalton's model along the way. Thomson's cathode ray experiment. He ended up basically running electricity through a tube here that had a fluorescent screen on it, and it was evacuated. There was nothing in there. And when he did that, he realized that this beam that normally went from left to right in a straight line, as you see in the picture here, that beam reacted to a magnet. And he said, well, something must be in there that's negatively charged that can interact with this magnet. And when he brought the positive end, and this is important, hint, hint, when he brought the positive end of the magnet, the beam went up. And he concluded that since they're attracted, the beam must be made of negative things. And when he flipped the magnet over and he put the negative side of the magnet, the beam went away because the beam was also negative and they repelled. So that's how he concluded that there were little negative things. He named them corpuscles, but they were later named electrons. And he changed Dalton's model from the solid model like the bocce ball to something more like this, where you have a sphere, you have all this positive mass. This is like the dough in your chocolate chip cookie, and these are like the chips or the raisins in his plum pudding model. So he said there's little electrons stuck in this positive dough, and that was his plum pudding model. His student came along, Rutherford came along, and ran an experiment in which he shot tiny positively charged alpha particles. You now, after doing the nuclear section, know alpha particles are really helium nuclei. So it's got 2 protons and 2 neutrons and no electrons, so it's positively charged. So he shot these little alpha particles at the piece of gold foil. He expected them all to go through. He just thought they might go on different little angles over here, so he set his students up to measure the angles. And lo and behold, they realized that not all of them went straight through. Most of them did, and they concluded most of the atom's empty space because most of them go right through. But some of them get deflected on weird angles, or even right back at the source. And they said that something dense in the center of the atom must be there to cause those little particles to ricochet back. So the nucleus carries most of the atom's mass. It's very, very dense. Remember, you ran the little simulation where you took marbles and rolled it at other marbles. If you rolled them at cotton balls, if it wasn't as dense as a marble, you would get different results. They wouldn't have ricocheted back at you. But since they were so dense, it was able to bounce right back. Same thing with the nucleus. And he also concluded the nucleus is positively charged because some of these guys went near and then veered off because positives repel positive. So he deduced that there must be something in the center of the atom that was very densely packed and positive, and the rest of the atom is empty space. So that's his big contribution to the model of the atom. Then the quest was to find out what happens with these electrons. Do they just sit there? Do they move? Do they go around on orbits? What happens? And Bohr came along and he played with the emission spectra that we looked at, the absorption emission spectra, and he realized, at least for hydrogen, that it worked perfectly. You can get that electron excited, it moves up to different energy levels and then drops back down. And he thought they were on predictable paths, and it was easy to predict exactly where it's going to jump to based on what color it was giving off or how much energy absorbed. And some other guys later on came up with the quantum mechanical model. They used his idea and they built on it. And they basically said that he's kind of on the right path. Yes, electrons do travel in certain regions, not on paths, orbits, but in regions. And then they can jump from one region to the next if they get energy, and they can fall back down and give off light. So they took his model, like I said, and changed it quite a bit. And the biggest difference is the idea of an orbit. It's not on an orbit. It's in a certain region. We now know those regions are energy levels, and then we can break those energy levels down further into sublevels, and then we can break those down into orbitals, not orbits. And those are, again, the SPDF and the areas that all combine to make this fuzzy electron cloud. But the big idea is that we don't know with certainty. Bohr said we know exactly where it's going to be. The quantum mechanical model, all the math that supports it, says that we can predict the probability, use math to predict the probability of finding an electron, but we don't know exactly where it's going to be. And simply looking at an electron is going to end up moving it. So it's not going to have the same properties it had before we got to see it. So we really can't be certain about it. So there's a level of uncertainty with this. But we know where they're going to be most of the time, usually when they're in their ground state, when they're not excited. And that's kind of where we stand today.